Welcome to a video on Class B amplifiers. Right, so we're going to have a look at the BJT and MOSFET configurations simultaneously. So mostly the voltage transfer characteristic, the efficiency, and then that we can use it as a single rail, not dual rail as the Class A amplifier. Then there's some ways to improve the Class B, and lastly some advantages and disadvantages before we get to the simulations. Right, so the Class B amplifier is probably the most efficient of the lot, but it has one small problem, and it is that it has crossover distortion. So to understand where this comes from, we need to look at the schematics. So on the left is our BJT, on the right is our MOSFET configuration. Right, so we have a NPN and a PNP transistor complementary, so we typically want them to be roughly the same. And you'll notice that there is no bias on the input right here. So we have a VBE and a VEB here that is not being utilized. Okay, so if we have a positive half cycle, the top transistor will conduct. If we have a negative cycle, the bottom transistor will conduct. Okay, so this is what push-pull means, is only one transistor will be active at a time, but due to the bias not being here is why we have this crossover distortion. Right, obviously for a MOSFET the crossover distortion can be much larger due to a bigger bias being required here between the two transistors. Okay, so since there is no extra biasing going on, we are using these transistors at their peak efficiency. Right, so on the voltage transfer characteristic, a BJT typically switch on at 0.5 volts, not the 0.7 that you usually think it would. And so here for the 1 volt here in the middle, we call this the dead zone. So anything that goes in, nothing will be coming out of your amplifier. For the rest, you have 1-to-1 transfer, and the maximum input and output is described here. So the maximum output is still just the rails minus the saturation. The maximum input is the rail minus the saturation plus the VBE voltage of the transistor, so the on voltage. We have something similar for the MOSFET, so here in the middle it will be the threshold voltages. Again, we just subtract the load and the on resistance of our transistor here at the top, so we can reach the rails technically. And for the maximum input, we just add the threshold voltage. So for all intents and purposes, with a very small RDS value, these will just disappear from your graph. Okay, so for the BJT, our maximum input is 10.4 or minus 10.4 volts, similar to our Class A amplifier, plus minus 9.7 volts. For our MOSFET, plus minus 10 volts on the out, and for the transistor that I used, they are matched. Threshold voltages of 1.1 volts, So our input here can be 11.1 and minus 11.1 volts. Right. So the efficiency transferred to the load is the maximum peak square divided by the load. Only one source at a time will be doing work, and it will be doing work according to the sinus wave that is coming in. So it is 1 over pi times our peak output over our load resistor multiplied by our source, our VCC. Since this will be symmetrical, our total source power is 2 times this equation. And at maximum efficiency, our peak output and our VCC will be roughly the same. That is. Um, so calculating this, our efficiency will turn out to be pi over 4, which is 78.5%. The maximum that we can transfer to the load is VCC squared over 2 times our load. Okay, so this is a very efficient configuration. The only problem with it is the crossover distortions. There is not much designing to do. The only design work that you have to do is to ensure that the transistor can handle the amount of power that it's going to have to supply. Right. Single rail usage. You need to apply offset on the input, about half times VCC if you want to use it as a single rail application, and you need to put in a capacitor on the output to remove the DC offset on the output side. Right, now we can improve our amplifier by putting it in the feedback of a op amp. So this op amp is in a buffer configuration. So the output here is going to the input, and the input is going into these transistors. By the way, this is how you increase the output current of any operational amplifier. If it can't supply enough current, is you can add transistors here on the output. Okay, but since we are building a driver circuit, we use the op amp in a buffer configuration, and the only thing that it does is op amps and feedback tends to linearize distortions. So the dead zone that we're having is a VBE voltage right here, or technically the 0.5 volts, but let's go VBE divided by the gain of the operational amplifier. So if infinite gain, this distortion can disappear completely. It will not disappear completely, but roughly. So with an amplifier of a gain of 10, it will be what? 70 millivolt dead zone. Gain of 100, 7 millivolt dead zone. And so on and so forth. For the MOS, the threshold voltage gets divided by the gain. So by having this in a buffer configuration, the dead zone will be decreased by the gain of operational amplifier. Some things to note: the output swing will be limited with the op amp saturation voltages. So if this is plus minus 10 volts and the op amp has a saturation voltage of 2 volts, it will now become plus minus 8 volts. Right, you also need to consider the slew rate of the op amp, since this is maximum outputs of operational amplifier, it needs to have a decent slew rate. Right. Advantages and disadvantages. So it is a very simple design. You just slap in two transistors, calculate their power, and there you go. It is 78.5% efficient without the huge power losses. There is no offsets, and it can be used in a single rail application, but you need to apply offset for the single rail. The big disadvantage is this output distortion, deadband, crossover distortion, whatever you want to call it. There is a couple of terms that people will use for it. Is a huge disadvantage of the Class B amplifier. Right, let's go and have a look at some of our simulations. Right, so here is our simulation of our Class B amplifier of BJTs. So I'm inserting a 10-volt signal. First just the DC. So almost to 10, 11.1 maximum input, and the dead zone. Okay. So here we can clearly see the dead zone in our output and the distortion. So versus our input, so it becomes a little bit smaller than our input originally was, 5.7, 0.5. So we have a bit of a decrease in output voltage due to that. And just to make the distortion clear, if we do FFT, here's our original signal, and we will have these harmonics starting to exist on our output due to that dead part. Let's have a look at the FFT of a normal signal, and here you can see that there is no harmonics at all. Okay, so if you do a Class B amplifier, you also need to go and check out the percentage total harmonic distortion. There is a video on that with oscillators, how to calculate the total harmonic distortion. So yeah, our output here, let's close this, I want to split view. Our output here of our distortion, if we make this 11.1 on the input side, we can reach our rails. I didn't account for the saturation here, so if we go to 10.7, where we have rail to rail outputs. Okay, other than that, there is not much to show for a Class B amplifier. Okay, so here we can also clearly see one transistor conducting one half and the other transistor conducting the other half of the signal. Okay, let's open our single rail and then our op-amp configuration. Right, here I have a single rail application. I apply a 5V DC offset and half the rail at the input. So this is our input signal. So it is with a 5V DC offset, plus minus 10 volts, plus minus 10 volts, and there is our output with DC removed with this capacitor right here. So here's our normal signal. We can probably increase this input a little bit. Not that much. Call this 5.5. We can get decent outputs even for a single rail application. Okay, so this can also be the output of an op amp if and this is you must apply feedback for this to work properly, and the operational amplifier must have a very large gain to correct this output. Okay, so it can be a all-in-one kind of deal, but this is not very common for op amp output stage due to this distortion right here. So yeah, let's have a look at a different simulation. I just put a little something together. If you don't want to add a DC offset to the input necessarily, you can do DC blocking on input and output and just put two big resistors here of equivalent size. That will do your DC offset for you. Add the 5 volts and the output result will be very similar. Okay, so if you need to put this somewhere and you can't supply the DC yourself from a previous stage or whatever, you can do it like this, but you sacrifice um, low frequency in the bandwidth for doing this. Right, so this is almost halfway to becoming a class AB amplifier because this is almost applying a bias. But yeah, so moving on. Here is our op amp configuration. Here is our input plus minus 8. Here is our output plus minus 8. You almost can't see this distortion, but it is still there. So if we do a FFT on the output, need to select that first. There is still harmonics, but there is much less of them and they are more suppressed than in the class B without this feedback right here. Just as a note, if we were to go and make this 10 volts at the input now, it will start clipping because this op amp is being saturated on its output and it clips. Okay, if you want to know if slew rate is a problem, if you use your op amp and suddenly the output becomes triangle waves, not this clip, but these starts to become triangular, the slew rate of your op amp is too low. Okay, so you get triangles, slew rate. Always the slew rate. Most people forget about slew rate. So yeah, that is how to improve our Class B amplifier. So it's improvement, it's not a fix for the distortion. Let's go and have a look at our MOSFETs. Right, our MOSFET Class B, you'll see that the dead zone is much larger, but we get closer to our rails. Oh, this one was 11.1. That's where I went wrong earlier. I forgot. Okay. So in the transient, we get to our rails if we apply this 11.1 volts, but we have a much larger distortion to worry about in this amplifier. And if you don't pick your transistors symmetrically, you can have other problems. Let's pick one at random. This one has a threshold of 1.1. This one has a threshold of 3.3. Let's choose that one. And now suddenly this becomes way more distorted. And look at this output right here. Minus 10, 8. It's not even balanced anymore. Okay. So you need to be careful and select your MOSFETs to match. They really need to match a lot. So if we look at the voltage transfer, 1.1 here, 3.3 volts right here. Okay, so don't ever get caught in that trap. Match your transistors. Okay, let's have a look at some of a single rail and then the improved version. So here is our single rail application. 5 volt offset. Let's run this. Input, output. There's a lot of losses on the output for this because it's MOS and the threshold is much higher than the BJTs. But again, you can have better thresholds and this will improve up to a point where it can be better than a BJT application. But we have more distortion here because our threshold voltage is much higher than the 0.7 of a BJT, and you'll find that we have more harmonics for this one. Okay, any case, let's go and have a look at the version with the op amp. Right, our MOSFET application, if we run this, let's see what we get. There's our input and our output is aligned. Some issues that you might find with op amps here, if you pick the wrong op amp, don't go for JFET input op amps. Rather go for a op amp that has BJT inputs. Sometimes your simulation, if you run it, will start to take minutes for every couple of microseconds. That means that your op amp and your output stage together has started to create some form of oscillations. I found that that is typical with your JFET input operational amplifiers. So you're going to have to play around to find one that does not cause your circuit to start oscillating. Right, so that's one thing to look out for. But the same deal, rail voltages, slew rate, etc. goes for this circuit right here. So you'll see that I inputted 8 here again. If I make this 10, the operational amplifier will saturate. And there we go. Input, operational amplifier has saturated. Right. And if we zoom in, again, our distortion did not disappear. It just became much smaller. Right, and that is it for class B amplifiers. Thank you for watching and see you in the next video.